All right, so today's mission is to do a little machine work to these beadlock wheels for the Scout. And I'll explain to you what a beadlock is. When you're doing off-roading, rock crawling, even going on to a sandy beach, it is ideal to have your tires aired down as low as possible, basically. Because what happens is, if you have a tire that is inflated rock hard, and the vehicle is sitting on the ground, it is going to form a radius with the ground. Very little contact. But if you notice on that tire, see how it's squatting down? That tire has a low air pressure in it, and it allows the bottom of the tire to conform to the surface it's on. If you're on a flat surface, it makes a big flat contact patch. If you're going up around a rock, it will kind of conform to the rock and grapple around it. So, in order to deflate your tires, you let the air out. The problem with that, it is the very air inside of the tire that keeps it held to the wheel and keeps it sealed with the wheel. There's no tube inside of one of these modern tires. So, when we let the air out, down to a low pressure, the tire has a tendency to what we call unseat from the bead. So the bead is this area of the tire right here, and on a normal wheel, this would be wrapped around by the steel or aluminum of the wheel itself. So here's a junk tire. You can see how the wheel wraps around the tire and the rubber's underneath it. When it inflates, it forces against the wheel, creating a good seal. When you let the air out, you don't have enough pressure to maintain that seal, and the tire deflates at the worst possible time. So the solution is to use a wheel that is called a beadlock, and that's what we're looking at right here. This wheel, basically, the tire is on the outside face of this surface right here. And what we were going to do is clamp the bead of the tire to this surface under a lot of force. And that way the pressure in the tire can be lessened and you still maintain a good seal. Keeps the tire from slipping, and you can do some hardcore off-road action. So this is a beadlock ring, and the ring is secured to the wheel with 32 bolts. All right, so I'm going to rotate this so it lines up. All right, so one of those bolts goes down through there, and then if we look around underneath, the bolt protrudes, and we put a nut on the other side, and we do that 32 times around the wheel. That would normally be wonderful. The problem that I'm facing with this wheel is it was designed for a tire that had a thicker bead. All right, so I'm running these Toyo Open Country mud terrain tires, and the bead here has a thickness, but adjacent to the bead is this anti-coning lug. So the idea of what's supposed to happen is this piece of metal and this piece of rubber are basically supposed to be the same height. And that way, when we put 32 bolts in here and we torque them to spec, the beadlock ring itself basically stays flat. It doesn't turn into a cone. If this was not here, all of those bolts and all of that force would cause the beadlock ring to cave in or turn into a cone. So by having this here to jack up the other side of the bolt, it allows good force and distribution of force onto the bead itself. We have a anti-coning lug that is too high. All right, and this tire has a bead that is too small for it. The solution, we could get another tire. That's not happening. These are pretty expensive. We could machine down these lugs so that they are shorter. That would require me dismounting all 4 of the tires that I already have mounted, putting them in a mill and machining them down. That's quite a bit of work. The other problem with that is if I ever do change tires and I end up with one with a thicker bead, unfortunately the wheels will have been machined to the bead thickness of this one, and it kind of doesn't allow those wheels to work as well. So I came up with an alternate solution. I decided that if I took the beadlock ring and I flipped it over, you can see exactly where those lugs were contacting this ring. If I machined a slot that was the difference in thickness between the two so that the beadlock ring could sit lower, it would be a great solution, because I could use this ring in that position. If I ever get a thicker tire, I can turn this 22 degrees or whatever it works out to be, and I could put it on a surface that has not been slotted. So that's what we're going to do. I kind of drew on here with a Sharpie roughly what that slot's going to look like. And this has 8 of these surfaces around the wheel. So 360 divided by 8, we got 45 degrees in between each one. So we're going to write a program, and it's going to cut the slot. So the slot at 6 o'clock position would be here, but then we're going to take that slot that we program and we're going to rotate it to here and over to here and so on and so forth all the way around the ring. And we're going to utilize the rotation feature that we can program into a CNC mill. Okay, so I have the part sitting on the mill table. I have not bolted it down, but I am kind of getting an idea of how much axis travel I have. Now, of course, I am shy by 2 inches in the Y. I have 14 and I need 16. I've got plenty of X, but it's the Y that's going to catch me. So what I've decided to do is to break this down into 2 different parts. We're going to mill this one, this one, this one, and this one. Okay, that's going to get us 4 of the 8. In other words, we are going to be able to mill 4 of the slots of the 8. We're going to rotate the part 180 degrees and use the same program to machine the other 4. So this is basically what the program is going to look like, and I'm going to show you how I program that using rotation next. Here we are in the simulator. I've written a contour that uses an end mill, and it goes around in this oval shape. I chose to do it this way instead of plunging the tool and going right down the center to create the slot. It's better to use a smaller tool and to actually turn this into a pocketing or a contouring toolpath. Gives us better surface finishes, better accuracy, and so that's what I ended up doing. The result here is basically to give me a slot exactly to the dimensions that I want. So I wrote that one instance. Now, we need to do 8 of these that are rotated around that circular part. So there's going to be 8 instances. Each one is at a different position on that circle. And we have a trick for doing that. Our programming codes in FANUC formats allow for a G68 code, which will rotate everything that you program on the coordinate plane. So this is pretty slick. And just to take you through the program before we incorporate that, standard stuff, program number, safe start, we load the tool, we rapid to, I have it rapid into the center position of the circle, which I've defined as the origin.
All right, so in other words, to zoom out, this is the center of that circular part. Now you can't see the part on here, but that's the center of it, and this is where the one slot is going to be machined in reference to that. And just to help you visualize what the part's going to look like, I machined the circle that represents the part around here. I programmed that. I have it going to X 8.5, Y 0, and then cutting a full circle. So that kind of helps visualize where this slot is in relation to everything else. So I went out on the machine and I mocked up this setup, and I discovered that with the size of the part and where the column of the machine is, I don't have enough travel to get to this one slot. I'm short by like half an inch to an inch. So I think I mentioned earlier, what I'm going to do is I'm going to cut this slot here at the 3 o'clock position first. And I'm going to cut the slot here. And then I'm going to cut the slot at 12 o'clock and then the slot here. That's going to give me 4 slots. And I can rotate the part later 180 degrees, cut that same program, and that will give me access to the other 4 slots. Okay, so unfortunately, I programmed the first slot here at 6 o'clock position, which is a position I can't even get to. So I could reprogram that slot contouring operation for a vertical orientation right here at 3 o'clock position, or I could invert all of my positives and negatives and cut it up here at 12 o'clock position. Positive and negatives in the Y, I should say. But I'm going to go ahead and just jump into the benefits of the G68 code, and I'm going to rotate that slot exactly where I want it. Okay, so I'm just going to create some space in my program. This movement right here, this positions it rapids to that very first start point for the slot. Okay, and then it plunges to depth, it feeds linearly in the X, it cuts the arc, feeds linearly, no, it cuts another arc, feeds a linear arc, and then it lifts up. Okay, so this package right here is everything that is utilized in order to cut that one slot. So what I'm going to do is I'm going to take that one slot, I'm going to rotate it. So right before that operation, right before that sequence of operations that cuts the slot, I'm going to throw in a G code that is G68. I am going to put the X and Y position of the center of rotation. In other words, I want my slots to rotate on this circle, and the center of the circle is smack dab in the middle of the part at X0, Y0. That is the center point of rotation. If you were to draw this circle, that's where you would put the compass point. So I'm going to call that center point of rotation X0, Y0. And then finally, I put an R value in, and R doesn't mean radius here. In the context of the G68 line, R means rotate. So I'm going to put the number of degrees that I want it to rotate. And right here is where it created the first one. I don't want it to be here. I want it to be 90 degrees out of phase from here. So my rotation angle will be 90 point. And did you see what just happened? That was it. That's all I had to do. G68, the center point of rotation of the origin, and R, the number of degrees that I wanted it to rotate. And then it rotated the whole coordinate plane and it ran down through here and cut out that slot. Okay, so that is the first instance. I'm just going to put a little break here. Rotate and cut slot 1. and make it real visible for everyone. And I'm going to copy this, and at the end, I'm going to end of that particular, I don't think I copied it right. At the end of that particular operation there, it is going to get another flag, another marker, and we're going to call this, just call it end of slot 1. All right, so it's real plain to see what's going on there. Then the next thing I should point out is I could use a sub-programming technique. I could use a macro technique. I'm going to keep it simple. I want you to focus just on how this G68 code works. So I'm going to copy it, right? I'm just going to right-click, copy, come down here, right-click, paste. So I get another iteration there. And let me put some space here to separate them. So this is going to be where we cut slot 2. And I'm going to change those headers. And really the only thing that's going to change is my rotation angle. So instead of 90 degrees, my rotation angle is going to be 45 degrees further than the one it just cut. So in other words, the one that was just cut was cut at 90 degrees. The next one's going to be cut 45 degrees further than that one, for a total of 135 degrees from where that first toolpath was written. And there we go. So we can see that slot in position where we want it. I'm going to copy this, and we're going to paste another one. This is going to be for slot 3. And here we're not going to use 135 degrees. We are going to go 45 degrees further, and that would be a total of 180 degrees. So there you see it. So slot 1, slot 2, slot 3. And now I'm going to go on to the next one, slot 4. And this is going to be the final one for this program. So we are going to take 180 and we're going to tack on 45 degrees to it, which is 225 degrees. And that gives us the final one that we're looking for. So slot 1 here, slot 2 here, slot 3 here, slot 4 here. That gives us half of the slots that we need. So when I get out to the machine, and I'm going to cut them because I have travel to get to those, and then I'm going to rotate the part 180 degrees, and I'm going to, on the same part, cut the same program at different orientation, and that's going to give me slot 5, 6, 7, and 8. Okay. Now there's one thing I want to clean up here, and I have it going, it's rapiding right here to that position. So I think up earlier in my program, yeah, right here, it's doing a positioning move to where it thought the very first slot start position would be, which was this guy. But at that point, there's no coordinate system rotation yet. So I'm just going to delete that. That's a little bit redundant. And hopefully that goes away for me. There we go. That took a little while. All right, so just to recap, G68, pretty simple. You throw that code in and you give it an R value for how much you want it to rotate your coordinate system. Everything that you program is going to go for a ride on an angle. Okay, and we define where the center point of rotation is for that whole rotation scheme. And I use the origin because conveniently that's where I place the origin on the part right in the center of the whole works. And that's it. So now we're going to give it a try on the machine.
So I've mounted up a Noga indicator. After clamping the part down to the table, I've swept around the interior surface. Now this is a laser cut part. So it is a little irregular. We've got a little bit of a draft angle or taper on the cut. So I've just gone around it and I've kind of gotten the indicator to be a happy average between all of these interior surfaces, and that places the spindle center line in the center of the part feature. I'm now going to call this X0, Y0. And now I'm going to bring the Z-axis down, and we're going to get a touch off of this piece of paper, and we're going to qualify the tool based on this position. Okay, and there's a light drag with the paper. That places the tool 4 thousandths away from the surface that I want to be Z0. So I'm going to qualify this tool accordingly, and there we go. All right, so we're going to try it. Okay, so looks about right. I've got to move that last clamp. I wasn't really thinking, and it's in the wrong place. So I'm going to move that, and then the scratch pass looks good, so we're going to go to full depth, and we're going to cut it. All right, fire in the hole. Everything has been cut. For this section of the part, we have 4 of these slots cut. Now we're going to rotate this 180 degrees, and we're going to do the other 4. So I thought I'd take a moment and show you a little bit about how I set this part up. I have these hold downs and step clamps, and you're all familiar with how those work. But these two right here are not merely clamps. What I did was I took some step clamps and I utilized them so they serve as a stop. So what's going to happen here is, as I need to rotate this part 180 degrees, I don't want to have to indicate it again. And in fact, when I get the second or the third and the fourth beadlock ring, I don't want to have to indicate those either. So these I have bolted down to the table, and when I placed this in here, I located it against there. That served as a V-block in essence, a vertically oriented V-block, and that aligns this right in place. So what I've got to do now is I've got to spin this 180 degrees. And when I put it into place, it should go something like that. It's going to cut this slot, this slot, this slot, and this slot, bringing us over to the last slot that we cut and completing the part. So theoretically, when I clamp this down, my XY location should be good. Now I am going to also show you how I went about orienting this, because I want these slots to be oriented with these holes, because they have to match up with the anti-coning lug that's on the wheel itself. So what I did, this is down and dirty for a machinist, but you know, we have to consider what our allowable tolerances are. On a wheel and tire, on a rock crawler, we're not required to work to 5 thousandths tolerance. We're sometimes not held to plus or minus 10. Sometimes it's far looser than that. And if you've ever seen a wheel and tire go down the road, there is a ton of run out, and that's acceptable. I can't quantify that, because it really depends on the nature of the application of the car, the size of the tire, and a lot of variables. But for orientation purposes, what I did was I dropped 2 bolts down here, and that allows me to get the orientation angularly, pressing it into the V-block, and then I can secure my clamps. And I'm going to verify this with the indicator, but I have pretty good faith that it's going to be within 10 thousandths or so. Again, this was a laser cut part, so the laser cutting process it's pretty good. It's far better than plasma, but it's a similar type process to plasma in that we're using a very hot column of heat basically to get the metal to turn into a molten state in a very localized area, and that's plowing through the material, blowing it out the other side and severing it basically. The thing that we want to do is also remember that those machines are not very precise. A lot of times their accuracy pales in comparison, just from a positioning standpoint, to a lot of the CNC machinery that you're used to. So I'm going to secure this. I'm going to double check that we have a relatively accurate XY location, and then I'm going to cut the remaining slots, and this part will be finished. Redo. We have all of these receiver grooves to match up with here. So I'm going to place it on, and we're going to put some bolts in it, tighten it down, and see if it worked. Okay. So there you have it. That is a completed beadlock wheel. It's been holding air for about a week now and no leaks. So we did a successful job modifying that, and now we are ready to go wheeling.